Welcome. The stage is set now for a very important lecture and a really powerful tool that allows us to solve a lot of the problems that we have solved already, but much more easily, and also allows us to solve problems that we haven't quite been able to solve before without the use of calculus. So it's the conservation of mechanical energy, and we'll start at a very familiar place here. Let's say we've got a ball of mass m. It's some height y above the ground, and it's going to fall towards the ground due to gravity. And we draw a free body diagram here. We only have mg acting on the ball. So weight, we know, or the force of gravity, is a conservative force, and we also know that the net work acting here is equal to the change in the kinetic energy of the ball. Well, since gravity is the only force acting, and that is a conservative force, then we know that the work done by conservative forces is equal to the change in the gravitational potential, and that's the opposite. So here we've got the change in K is going to equal the opposite of the change in U, since the work done by all of the forces acting in here are conservative forces. So solving for this, we have the change in K is not equal to, but added to the change in the potential is equal to 0, which means that at any time during this ball's drop, the total kinetic plus the total potential is going to equal the same thing. Said another way here, we've got K final minus K initial plus U final minus U initial equals 0. Move the both initials, K and U, to the other side, and we have K final plus U final equals K initial plus U initial. So this means that the total energy at any initial time is equal to the total energy at any final time. And this energy specifically is called mechanical energy. And mechanical energy is conserved when only conservative forces are acting. So let's define mechanical energy, and these are the three kinds of energy. Mechanical energy. These are the three kinds of energy that we've already encountered. There's K, there's gravitational potential, and there's spring potential. So if mechanical energy is conserved, and mechanical energy is conserved when only conservative forces are acting on the object. And we showed that here because the only force acting on the object is gravity, and gravity is conservative, as we talked about in the last class. So since only conservative forces are acting, then we can say that mechanical energy is conserved. So the kinetic energy plus the gravitational potential energy plus the spring potential energy at any initial time is going to equal the kinetic energy plus the gravitational potential energy plus the spring potential energy at any final time. Now, there are a couple conditions that have to be met when we say that mechanical energy is conserved. So mechanical energy initial equals mechanical energy final. We already talked about one of these conditions, only when non-conservative forces are ignored. All right, so mechanical energy is only conserved when we ignore non-conservative forces, or when only conservative forces are acting. And the other one here is it must be a closed system. And when we say closed system, we mean that no external forces, no forces outside of the system are doing any sort of work to add energy to the system or take energy away from the system. So for example, in the ball falling to the earth, we're looking at the ball-earth system. Why do we need to include the earth? Because the ball falls due to gravity. And if the earth wasn't there, there would be no force of gravity making the ball fall. So in the ball-earth system, we can say that in the absence of air resistance, mechanical energy is conserved. This is a closed system. We're ignoring the force of gravitational attraction between the sun and the ball, and the moon and the ball, because frankly those are so small that we can ignore them. All right? So we need to make sure that those two conditions are satisfied for mechanical energy to be conserved. Let's look at some examples as to how conservation of mechanical energy simplifies problems that we've already seen. First, let's take straight up projectile motion. We've got an object launched from a cliff at an angle of theta with some v naught. The cliff is a height h, and the ball goes whee and comes down and hits the ground with some v final. It reaches some maximum height, capital H, above the top of the cliff. Now, if we ignore air resistance, which we did in all of these, then we know that E naught is equal to E final. The energy at any one moment of this projectile's path is equal to the total energy at any other moment. All right? And so we can find the final velocity of the ball using conservation of energy. First, and most importantly, we need to define our 0 point for gravitational potential. And we can do that anywhere we'd like. I'm going to make that level the ground right here. So that's 0 gravitational potential. With that in mind, then, we look at the energy at the start. We've got kinetic energy because the ball has a velocity, and we've got gravitational potential energy. Down here where the ball lands, we just have kinetic energy. All right, gravitational potential energy is 0 there. So filling in my energies, E initial, we've got K naught plus UG naught. And finally, we just have K final. Filling in our equations, K naught is 1/2 mv naught squared. And initial gravitational potential is mgh, the height of the cliff. And that's equal to 1/2 mv final squared. If we're solving for v final, we notice that the masses cancel out. There's 1 in every single term on both sides. So now we multiply by 2. We get 2 times v naught squared plus gh. And we're going to take the square root of that. There's v final. Plug in v naught, plug in g, plug in h, and you've got the final velocity of the ball. Very, very quick, easy, piece of cake, much easier than we dealt with when we were using kinematic equations to solve these problems. Now notice that the other types of problems we solve with projectile motion can also still be solved, remembering that the initial horizontal velocity doesn't change, so that means that we also know the final horizontal velocity. If we know the final horizontal velocity and we know the final velocity, we can find something like the angle that this projectile hits the ground with. We could also solve for the max height way up here because the ball is going to have kinetic energy, let's call it time 1, and it's also going to have gravitational potential energy at time 1. The kinetic energy, again, this Vx is the same as it was at the launch, which just happened to be V naught cos theta. So if we know Vx, we know the kinetic energy, and the height is going to be associated with the gravitational potential. So I could find the max height above the cliff. Okay? Things that it won't allow us to solve for are things like time. We won't know the time of flight. We'd have to go back and use kinematic equations for that. But for other things like this, conservation of energy vastly simplifies this type of problem. Let's look at another type of problem that we encountered previously, the Atwood machine. So here we've got an Atwood machine, massless pulley, massless strings, but we've got big M and little m. Little m sitting on the floor, big M is some height y naught above the floor. And we're going to release the system, and we want to know what's the velocity of the blocks when big M hits the ground. And we know that little m is going to have the same velocity going upward. So no friction, we can say that mechanical energy is conserved, so E naught is equal to E final. And this starting point, E naught is equal to E final, is for conservation of energy like F equals ma was for Newton's laws. The sum of the forces is equal to either 0 or mass times acceleration. This is our starting point. So we start here, and always we're going to define our level of 0 gravitational potential. And here again, I'm going to make it at the ground where little m starts. So then we ask ourselves, okay, what kind of energy or what kinds of energy does the system possess initially? And initially, it's just big M with gravitational potential energy. So UG initial of big M. And then finally, when these things are set in motion, little m's going to go up, big M's going to go down. Little m is now going to be in the air. It's going to have gravitational potential energy. So UG final of little m. And then big M is going to be at the ground, so no gravitational potential, but it's going to have kinetic energy. So that's going to be K of big M. So filling in what we've got here, the initial gravitational potential of big M is big mg times his height above the reference level. And the final gravitational potential of little m is going to be little mg times his height above the reference level. If big M falls by y naught, little m is going to go up by y naught. And finally, we're going to have the kinetic energy of, oh, I messed up. It's not just big M that has kinetic energy. It's both big M and little m. So let's add that in up here. We've got the kinetic energy of little m. That is, and I made it, that is the most common mistake made with this Atwood machine, only taking into account the kinetic energy of one of the masses. Both masses in the system have kinetic energy. So 1/2 little m v squared. We want to know what that velocity is, so we're going to solve. Unfortunately, it doesn't look like our little m's and big m's are going to cancel out here. So we're going to do some algebra. We've got big M g y naught minus little m g y naught is equal to, let's go ahead and pull that v squared out. We've got 1/2 big M plus 1/2 little m. Dividing by big M plus little m, so big M g y naught minus little m g y naught divided by the stuff in the parentheses is equal to v squared. Let's go ahead and take the square root. And that's going to give us the velocity of big M and little m when big M hits the ground. If we know that velocity, we can find the acceleration of the system. If we know the acceleration of the system, we can go ahead and find the tension in the string if we need to. So that is a bit simpler than we did it with Newton's laws. With Newton's laws, we had to find the acceleration of the system, then use a kinematic equation to find V final. Here we could do it in one fell swoop with conservation of energy. Now we'll look at an example of a problem that we could not solve with Newton's laws without the use of some complicated calculus, and we didn't deal with these at all because it's beyond the scope of this class. However, energy allows us to solve, conservation of energy allows us to solve these so much more easily that there's no reason to use Newton's laws. So here's a pendulum. I've got a mass on the end of a string, and the string is massless. It's hooked to the ceiling, and we're going to let this guy go, and he's going to swing back and forth. And we've all seen this happen. And the pendulum is going to have some lowest point in its swing, which you can't really tell because of my very bad arc. So let's kind of erase that and just draw the low point. So we've got this low point in the pendulum swing with some velocity going this way. And then it's going to swing all the way up over to this other side, the same height above that low point. No friction, so we know that energy is conserved. We've got E initial is equal to E final. And we set our 0 point of gravitational potential. I'm not going to set it at the ground because I don't know anything about the ground. I'm going to set it at that bottom point of the swing. UG is equal to 0 joules. So let's see here. Let's say we want to solve for what that maximum velocity is at the low point in the swing. Well, if we consider the place where the pendulum was released, then we've got some initial height above that bottom point, and we've got gravitational potential energy initially. It's released from rest, so there's no kinetic energy. And at the bottom, it's at our reference level, so there's no gravitational potential. It's just kinetic. So we've got mg y naught is equal to 1/2 m v final squared. And masses cancel out. We've got 2gy. Take the square root. That's going to be the velocity at the bottom. we can see here in the pendulum swing that when it gets to the bottom, we have all kinetic energy. As it swings back up to the top, kinetic is changed back into gravitational potential, and at the other side, we have all gravitational potential. If energy is conserved, this better be why not as well. We can solve for any part of the pendulum's motion. Right here in its motion, it's going to have gravitational potential energy and kinetic. And we would set the gravitational potential at one of the maximum amplitudes to the gravitational and kinetic at this point and find out other information. We can also find out some information about theta. I know that this is L over here, and if we draw a right triangle, this is L minus L minus y naught. And so we can use right triangle SOHCAHTOA to solve for theta. Okay, all sorts of fun we can have with pendulums. We could not solve those with our current understanding of Newton's laws. Another type of problem where Newton's laws are way more complicated than using conservation of energy are springs. We'll start with the easier version, horizontal springs. On a surface, no friction. Energy is conserved. All right, so we know that initial energy is equal to final energy. When we look at this mass spring system, we got some mass m coming in with an initial velocity. And the spring initially is at its unstretched rest position, its equilibrium position, and it has a spring constant k. So the energy that the system possesses initially is just kinetic energy, k naught, and the energy that the system possesses finally. Let's say we want to know when this mass comes in and compresses this spring, how far does the spring compress? And at that point, the mass has zero velocity. So then it's going to be all spring potential energy after that. And we do have to do a couple of things here. First, for spring potential energy, we have to define our place where the spring potential energy is zero. And unlike gravitational potential energy, you don't have a choice of where this is. It's always going to be at the rest position of the spring, the unstretched position of the spring, the equilibrium position of the spring, whatever you want to call it. All right? So that when that mass comes in and causes the compression of the spring, delta x, we know that the gravitational potential, the spring potential energy is just going to be 1/2 kx squared. So the initial kinetic energy of the system is 1/2 m v naught squared, and it compresses the spring 1/2 k times delta x squared. So with this right here, if there's no friction, energy is conserved, we can actually solve for all sorts of stuff. All right, we can solve for the reverse. If the spring was compressed initially and the mass is let go, what is that velocity going to be when it's out there? We can, if the mass is known and the velocity known and the compression are known, we could solve for the spring constant. All right, all sorts of good stuff that we can do there. Now, more complicated situation is vertical springs. And the reason it's more complicated is because we have to deal with all three kinds of mechanical energy here. So let's say we've got some mass m sitting up here, some height y naught above a platform connected to a spring connected to the ground. M is initially at rest. We're going to release it. It's going to fall. It's going to hit the spring. It's going to compress the spring. And there's no friction, no air resistance. So again, we know that the initial energy is equal to the final energy. We have to do a couple things here. We have to identify, one, where our spring potential energy is zero. And that's going to be at the unstretched length of the spring. And then we also have to define where our gravitational potential energy is going to be zero. Where is our zero level? And again, we can put it anywhere we like. It kind of depends on the nature of the problem. One natural spot to put it here might be at the same level where the spring potential is zero. And so let's say that this spring compresses by some delta y. And we want to know how much that compression is. We also have to define a spring constant for k. There is a spring constant here. So we fill in and talk about what kinds of energy we have at each of these different points. So at the start, the system has no spring potential because the spring is not stretched or compressed. We have gravitational potential because the mass is above our reference level, and we have no kinetic energy. So we're just looking at UG initial. And now finally, when the mass has compressed the spring, we still have no kinetic energy in the system. It's at rest. The mass has compressed the spring, so we do have spring potential energy. And because our mass is below our reference level of gravitational potential, we also have gravitational potential energy there. All right? So, filling these in a little bit further, we know that the initial gravitational potential is going to be mgy naught. And we know that the final spring potential is going to be 1/2 k times that delta y squared. That delta y is the amount of compression. And now, since we're below the reference level, my gravitational potential is going to be negative mg, and the amount that we're below is delta y. So here then is an equation that's going to relate our compression, delta y, to everything else. And you'll notice that we've got a quadratic here. If we're solving for delta y squared minus delta y, move the mgy over, you've got a constant term, you're going to have to solve the quadratic. You're going to get 2 answers for delta y. And you're going to take, for right now, we're just going to say take the positive answer. We're going to explain why this is when we get to simple harmonic motion, why there's actually 2 answers. And for right now, it's beyond the scope of what we need to do. But we can also solve, if we know delta y, let's say that we start with the spring compressed and release it. And how high is the mass going to go? We can solve for y naught using this if we know delta y and m. Notice also the mass doesn't cancel out in either of these spring problems. So please be careful with that. Don't try and cancel it out. So again, to review, start here, set your reference level. Where is your spring potential energy 0? Where is your gravitational potential energy 0? Fill in the types of energies you've got at the beginning and at the end. Fill in what you know. Solve for what you're trying to get. See you